Hello guys, today we are going to explore some examples of uniform circular motion. Now this type of motion can be applied to many systems. So for example, planets, moons, satellites, all of them are moving in circular orbits. Another example can be electrons orbiting around atoms or charged particles traveling in circles in some magnetic fields. So all of these are the examples of circular motion. But the example that we are going to explore today is of conical pendulum. Okay, so consider a rigid support, and from this rigid support I am going to hang a pendulum, and this pendulum is going to move in a horizontal circle. So particularly we are going to study about the motion of this pendulum in circular motion, right? Now consider a situation when this pendulum is at this position A, right? Now let's say this is the height of the pendulum or length of the pendulum, and the radius of the circle being traversed by this pendulum is r. Okay, now at this particular situation, let's say this angle is theta, right? Now we are going to study or look at all the forces that are acting on this pendulum. So the first force that is acting is vertically downwards, and that is the weight of the pendulum. This is mass times acceleration due to gravity if we are considering the observations being done on planet Earth. So if you go somewhere else, let's say on Jupiter, so you will be taking the acceleration due to gravity on Jupiter. So over here on Earth, acceleration due to gravity is 9.8 meters per second squared, right? Now, another force that is acting on this bob, or you can say the pendulum, is the tension force. We know that the forces in the strings are tension forces. So now I have to resolve these forces into horizontal and vertical components, right? To analyze the motion of this bob. So let's consider the horizontal components now. If this angle is theta, then this angle is also theta, which I'm going to mark in green color. The reason being they are alternate angles, as this line and this line are parallel to each other, right? So as we have already done in vector analysis, if you have any vector A, so the horizontal component is A cos theta if this angle is theta, and the vertical component is A sin theta. So similarly over here, the vertical component over here, this is t cos theta, and this is t sin theta. Okay, now over here in this particular situation, the horizontal component of tension will be the horizontal component in the horizontal direction is t sin theta, and there is no horizontal component of weight, so I'm going to take that as 0. Now let's consider the vertical component. Vertical component of tension is t cos theta. That's my vertical component of tension, and vertical component of weight is nothing but mg, right? Now the only force that is acting on this bob is towards the center, and that is centripetal force. Now who is responsible for this centripetal force? That is t sin theta, and that is equals to mv squared by r, right? We know that the centripetal force is given by this formula, which is mv squared by r. Now there is no resultant in y direction. That means net force in y direction is 0 only if the upward force is equals to downwards force. So I get two equations as t sin theta equals to mv squared by r, and another equation is t cos theta equals to mg. So the equation was t sin theta equals to mv squared by r and t cos theta equals to mg. Let's just divide equation number 1 by 2, and the overall equation becomes tangent theta, because sin theta by cos theta is tangent theta, and when I divide mv squared by r divided by mg, I'll get v squared by rg. So that's my resultant equation for horizontal circular motion, not projectile motion. Now let's apply this concept of conical pendulum on a question. Now read this question. There is a 250 grams bob of pendulum, which is tied at the end of the string, and it is being moved in a horizontal circle whose radius is 1.5 meters. So the first step is always write the known variables. Okay, so my first known variable is mass, right, which is 250 grams. Now, grams are not the SI units of mass, they are kilograms. So you need to divide this by 1000. So I'm going to convert it into kilograms. The next variable is the radius of the circle, which is 1.5 meters. And the next step it says is that it is going to complete one revolution in 3 seconds. So time period is 3 seconds. Okay. Now the first part, okay. So before we do the question, now what is required? We are required the speed. The next step we want to find is the horizontal component of the velocity. Okay, so sorry, not the velocity, tension. Then vertical component of tension. Then we need to find the resultant tension, that is the total tension. And then we need to find the angle made by the string with the vertical, right? So the next step is to draw the diagram. Okay, now let's say this is my fixed rigid support and this is my vertical. This is the bob which is revolving in the horizontal circle, right? Now, as I said that this is the tension on the bob, this is the weight acting vertically downwards, which is mg, and now if this angle is theta, then this angle is also theta. So this is the vertical component of tension, which is nothing but t sine theta. Sorry, not t sine theta, it is t cos theta. And the horizontal component over here is t sine theta. Okay, now the first step he's asking is to find the velocity. Now velocity is always distance upon time. So distance is the circumference of the circle, which is 2 pi r by t. So when I substitute this value, 2 pi times radius is 1.5 times 3. So let's solve this question and I get 3.14 meters per second. Okay, so that's my velocity. So what's the next part? Next part is the finding the horizontal component of tension. Now part B is to find the horizontal component of tension, which is nothing but t sine theta, and that horizontal component is nothing but the centripetal force. So what is that? mv squared by r. So the horizontal component is mass was 0.25, velocity we have just calculated in first part, which is 3.14, and the radius was 1.5. So when I solve this, we are going to get 1.64 tension. Remember to, if it's not given in the question, then keep your answer up till 2 decimal places. So second part is the vertical component of tension, which is nothing but t cos theta. Now this is equals to the weight of an object, right? Because this is the bob, this is the tension, this is t, okay, this was angle, this is t cos theta, and this is weight in the downward direction, and this was t sine theta. So from here it's clearly visible that t cos theta equals to mg, because there is no net force in the vertical direction. So if these two forces are equal, this is nothing but the vertical component of tension. So mass was 0.25 times acceleration due to gravity is 9.8, and when I solve this, I'm going to get 2.45 newtons. So tension is a force which is nothing but newtons. The D part is to find the total tension, which is nothing but the resultant will be the square root of the horizontal component of tension and vertical component of tension. So the horizontal component was 1.64 squared plus 2.45 squared. So when I solve this, I'm going to get 1.64. So this comes out to be 2.69 plus, sorry, so this comes out to be nearly 6. So, and when I solve this square root, I'm going to get nearly 3 newtons is my resultant tension. Now what was my last part? Last part was, so this is my D part. So last part was, how can you find the angle? Now you know that T cos theta equals to mass times gravity, right? So resultant is 3 cos theta, mass is 0.25 times 9.8. So when I solve this, I'm going to get 0.25 times 9.8 gives me 2.45 divided by 3. I get 0.816, and when I do cos inverse of that answer, I'm going to get my angle as 35.25 degrees. So that angle was this. So this is how you proceed with all the physical quantities in uniform circular motion. So I hope you guys understood the concept of conical pendulum. Now, if you understood that concept, then do subscribe Knowledge Hub for more interesting videos and easy way to understand the concepts in physics so that you keep on smiling. So press the bell icon button and keep waiting for more upcoming videos. Till then, stay safe, stay happy.